processes. It's like with the ALM. And it is in any case looking for exploiting much more key characteristics of our products and processes than in the past. This is again to secure the right time manufacturing, but also to optimize the maintenance of our machines. And as we are preparing ourselves to reduce large parts of our launches in the future, the other area is the notion of health monitoring systems, which are entering in our landscape. And as it is the case, for instance, for the company we are teaming off, which is Ariane Works, on the Themis demonstrator. It's a reusability concept for the first stage, where NRA is leading the approach of the future health monitoring system. So all this is the general background. These are all these important evolutions of the domains in the current decade for us, which will bring us to more competitiveness on the launcher market. We are convinced. And that is why I'm happy to see all experts reconvening each year in this conference, like in the GEC Connect today. And I'm really glad to be one of the first speakers. I wish you all the best to have a good exchange. Even we are not in the mood to have it in a physical one, but I think this will perfectly be covered by the moderation and by the management of the conference. Thank you very much for your attention.
Thank you, Ludger, for this introduction in this day. So we'll stay in the composite world, and we'll invite you back at the end of the session to answer the questions.
Okay, thank you.
Thank you so much, Ludger. So now let me come to our next presentation. And this presentation will be held by Jean Botti. He's the CEO of Voltaero, so a new player in the aerospace field. But Jean Botti is not at all new to this field. He has multiple facets, both in his education and career path. He is an engineer by education and holds degrees from several prestigious universities, so including MIT, Arts Métiers, INSEAD. So also did more than one MBA. So Jean Botti began, interestingly, his professional career in the automotive world. So first at Renault in 1978, before joining General Motors in the US, 1989. So when he returned afterward to France in 92, he was appointed General Motors Director of European Engineering for chassis components. And in 97, so 5 years later, he returned to the US to take the reins of the Delphi Corporation Customer Solutions Center, which he held until 2002. So he rounded out his time at Delphi as a business line executive for the powertrain production line, and then joined the aerospace field, namely Airbus Group, in 2006. So from May 2006 to March 2016, so this 1 decade, he was Airbus Group Chief Technical Officer. And in 2017, he left the corporate world to co-found Voltaero. So besides this career track, he earned a lot of great awards for his career achievements. So he received the General Motors President's Council Award, was elected as a Delphi Hall of Fame Fellow. He was named a Fellow of the Society of Automotive Engineers. And he even received the Pro Pilot Award for the Best Aviation Technical Development of the year 2015, which was the Airbus EFAN all-electric aircraft already in 2015. So Jean Botti is also the recipient of both the Medal of Honor from the French Civil Aviation Organization and the French Légion d'honneur. So he will present today in his video speech Casio, which is an airplane to help resolve the environmental equation and improve safety. So main item points within his presentation will be the importance of hybrid aviation and development of the Casio plane, the essential role composite material play in the plane structure to leverage on the additional weight from the batteries and electrical motors, the ability of composite materials to allow for complex shapes, and last but not least, he will show applications in cabin interiors and smart cockpits. So unfortunately, Jean Botti will not be able to be with us live. He is in the US, but he prepared this presentation to be launched now during the JEC Connect. So please enjoy his conference on Casio, an airplane to help resolve the environmental equation and improve safety.
Hi everybody, welcome to the JEC. I know this year is a bit special because we have, we cannot do it live, we have to do it again in a remote way. But I'm very happy personally to introduce you to our Casio airplane and to Voltaero. And very specifically because in this JEC, this composite conference here in Paris, it's very important, to see that the future is also built out of materials like composites, okay? Lightweight materials, including aluminum alloys, but also composites are the key for the future, and specifically for airplanes. So you will see, I don't speak specifically in my presentation about materials. I try to give a synopsis, of what our airplane is all about overall, but it's clear that it's gonna be filled about composites outside and composites inside. It's not an all composite airplane, okay? But it's kind of an hybrid in terms of the materials being used. And I think it's important that, the ones that are listening to this, you integrate this in the sense that you have to find the right value, the right value proposition, for something, that includes, lightweight material. So let's start with the first slide. So our family of Casio products resumes in three models. 330 Casio is 4 seats, the Casio 480 is 6 seats, and the Casio 600 is 10 seats. As you can see by the design, the airplane is very modular and versatile, and it's been basically made for configuring multiple configurations for serving customers, and with various mission profiles. We will come back to it. Our vision for electric aviation resides in 3 keywords: hybrid, which is a combination of electric motors and internal combustion engine, provide multiple sources of energy, from full electric, don't forget you can use this plane on full electric, to full hybrid when you have long distances to make. This is very dependent of the distance. And in the middle you obviously have mild hybrid, where you can use both energies, to extend the range. This is very dependent of the usage scenario. Okay, if you have short distances, use pure electric. Mid distances is mild hybrid, and long distance is full hybrid. The second word is modular. Okay, Voltaero family will be available in 4, 6, and 10 seats versions, utilized for commercial flights, point to point, for regional travel, air taxi charters, for example, utility categories, for missions like cargo, postal delivery, medical evacuation. Those are very important, I would say, tasks that our modular airplane can do. And finally, with private owners, like me, I am a pilot. I'm sure there's plenty of pilots that are listening to this presentation. So private owners, obviously, is also one of our targets. The third word I would like to mention is experience. And the Voltaero has combined years and years of experience now in electric aircraft. This is the third airplane we make, with our team. We started when we were all at Airbus in 2011 with the Cricri, which was, kind of acrobatic airplane. It was a one seat, and that was 20 kilowatt at the time. Then, still in Airbus, we made this historical flight in 2015 with EFAN, who was a two-seater, and it was 60 kilowatt aircraft. And finally, we have been flying, and we will show you at the end, in the movie, we have been flying our Voltaero Casio, equivalent the powertrain of a 10 seats, to 600. So between 2011 and 2020 now, we have multiplied the power by 30 even, 30. Our goals is built on three priorities. Number one, promote regional transportation, okay? It's an innovative way, sustainable and competitive, solution for cleaner and more efficient ways to bring communities together and business together. And when you think about COVID, COVID has changed dramatically the way we're maybe thinking to fly. So, second priority is develop an aviation ecosystem. As I said, we want to remove, aviation from the environmental equation, and this is very important. And we want to do it also based on an e-flexible and on-demand flight network, utilizing artificial intelligence, basically, that can be enabled through smartphones, and teaming with also a French partner for airport infrastructure. French, or can be any part in the world. Today we are starting with France, but we want to be able to have the airspace support services and customers interface through that. So that's very much something that we're looking forward to. And finally, ensure Europe's position in e-aviation. In Europe, we want to be part of the development. And this plane is made in Europe, but I should say we're very open to make it everywhere in the world through licensing. We're looking at expanding. So it's going to be made in France to start with, but rapidly we'd like to make it all around the world through licensing agreements. The key performance characteristics is to be safe, affordable, quiet, and with low emissions. It enters into the category that we call CS23. It's got 3.5 hours of autonomy. The range can go up to 800 miles in heavy hybrid. Takeoff and landing distance much less than 1,800 feet. 3 power levels, I said that before, 330 kilowatts for the 4 seats, 480 for the 6 seats, 600 kilowatts for the 10 seats. 200 knots of cruise speed, so 360 kilometers per hour. That's what we are looking at for a cruise speed, and 20% lower emission than competition in full hybrid mode. That means when you use your airplane in full hybrid. When you're using it in pure electric for short distances, obviously you got 100% of low emissions. So, a revolutionary airplane and ecosystem comes together. This is the agreement, the partnership we have with Kinecter, a US company, to develop a clean and on-demand regional flight services with the Casio aircrafts. Kinecter is a flexible on-demand network that uses artificial intelligence, enabled through smartphone applications. And I would picture them as the Uber of the air. Casio aircraft will be integrated with Kinecter short-haul infrastructure. And our artificial intelligence will balance passenger demand with air transport availability. Okay? Kinecter software platform will interface directly with Casio Intelligent Cockpit, and this will show it in the future how we're going to do this. So, when you got this, I would say software, that is embedded into your airplane and that can, drive customers and pick them up and optimize, like I said, and Uberization basically of the era, you need another dimension, which is the ecosystem that helps us, to pull all this together and get the infrastructure in the airports to be able to achieve that. Voltaero and Edis is a French company that manages 20 airports in France, have the goal of developing sustainable and regional air transportation with our Casio aircraft. And we will focus on developing an ecosystem for short, medium, all air services. Voltaero will supply the Casio aircraft, while ADAIS will provide the resources such as airport infrastructure, airspace support services, and customer interface. The joint vision includes encouraging the creation of associated distribution centers, training schools, and maintenance, repair, and overall facilities. This is the third very important step into our journey. So we, in the next slide, you'll see that we have received the seal of excellence from the European community. It's funded by the Europe's Green Deal Strategy and Recovery Plan. To support the development of Casio aircraft family, we were chosen by the European community for an initial 2.1 million grant, euros obviously, and also designated for blending financing at a higher value that includes an equity portion up to 11 million. So we're very proud of that. The jury has said that Voltaero was among the very top-rated company, and we were among 2,077 candidates. And for this blended financing, I think only 25, all kind of industry included, were selected. So we're very happy, and the jury said at this stage it's a real innovation to the cycle of the sector and has the potential to impact the market. And there was also the recognition that the team is extremely knowledgeable and experienced in the establishing in the aviation industry. So this was very good for us. I would like to show you Casio 1 numbers compared to the Casio 2 600 that will be the 10 seats for production. So the numbers tell the story. Casio 1 is a parallel hybrid, 230 nautic miles and 600 kilowatts. This airplane has got more than 50 hours of flight. It's an integrated airplane with improved aerodynamics. You just look at the front nose, as you can see in the picture, in the top left. Distributed propulsion. This experimental airplane with 3 seats for test pilot and accredited engineers is the longest hybrid flight performed at this stage and the most powerful one with 600 kilowatt, as I said. We will move then into the new Casio 2 that will take a lot of learnings from this Casio 1. Parallel hybrid still, 670 nautic miles instead of 230, and we will get to 600 kilowatts. So Voltaero patented power module with 600 kilowatt of available power is the highest performing hybrid electric propulsion system flying today. Casio 2 will have the new improved aerodynamics necessary for high range, fuel efficiency, and speed performance. We're planning to go in cruise at more than 200 knots. Its parallel hybrid design is key to Voltaero's strategic for a modular a la carte aircraft family with 4 to 10 seats, and Casio 2 will be our serial airplane. The importance of composites, as you can see in this slide, is going to be crucial. Why? Because in fact, in a hybrid airplane, you're going to have to, I would say, compensate the overweight brought by the electric motors and the batteries, which makes, an hybrid airplane. And you're going to have to compensate that by savings into the materials. So, concerning Casio 2 or a production airplane, we're really thinking about having a cell that is going to be in aluminum alloy. That means the cockpit. I mean the outside, the structure. But everything has got to do with the wings, the canards, the booms, also, the empennage in the back. We're really thinking having this all made of composite to save weight. And this is a combination that offers the best in terms of electromagnetic interference, electromagnetic compatibility, also, lightning resistance, and at the same time, lightweight. So, we think about this essential role that composite could play in various aspects of the structure. And in addition,
we're really thinking about the ability of composite materials to allow for complex shapes. And we have many of those within our airplane. Outside, in the wings, the canards, but also inside. And inside, we're really thinking about application of composites, that are maybe not in fiber, I would say, like carbon fibers that are going to be applied outside, but more internally, we're thinking more in glass fiber. We're also thinking about wood composites that are really beautiful and makes very light structures too. So those are applications that we're looking, to make our interior cabins very smart, very nice, and at the same time, outside, in the structure, make it, I would say, composites that are very technical. So as you can see, there is many things that we are thinking about imitation of these composite materials.
Well, I hope you enjoyed the presentation about Casio and Voltaero. As you can see, the future is tomorrow morning, since we're planning to be in production in 2023. Keep following us, at www.voltaero.aero. There you have all the latest news and the greatest about us. And I wanted to thank you all, to follow this presentation. I hope you enjoyed it. I hope you enjoyed this new green aviation that comes, very soon here. And we're looking forward, to continue the journey with you folks. And I'm sure you'll have plenty of others, conferences you're going to be able to attend here, because it's so vast and so diversified a conference that it's really appreciable. I'm going to do that. So have a nice day.
Yes, thanks very much to Jean Bauty for this great presentation, switching from cell phone to presentation. And just to give an update, we are now over 300 people online from all over the world, as I see in the chat. So great to have all of you here in virtual, and of course, I really hope that we can meet next year in Paris in person. So now we will stay in the propulsion field, and we will introduce our next speaker, which is Scott Finn. So Scott is currently working at GE Aviation. He holds a bachelor, master and a PhD degree in aeronautics and astronautics from Stanford University. He has over 30 years of experience in the composites industry. So he started his career at Boeing and joined GE's research center in 1995. So he was there first involved in composites product development across all GE businesses, but mostly regarding fan blades and fan cases for aircraft engines and wind turbine blades. So he moved to GE Aviation's Chief Engineer's Office in 2012. And in that capacity, he oversaw development and certification of the industry's first ceramic matrix composite aircraft engine on the LEAP and GE9X engines. So he currently serves as Chief Consulting Engineer for composites at GE Aviation, as I was telling. And in his presentation about composite applications in GE Aviation engines, he will speak about the legacy and new composite components in Aviation engines in general. Then he will come to the topic of durability of composites in engine applications, especially with those CMC products. And last but not least, he will tell us about the range of materials and processes. So Scott, just like Jean, is based in US, so he couldn't make it live. He also recorded a great video so that you can enjoy it now. And we'll see each other for the last speaker right afterward. Enjoy.
Hi, I'm Scott Finn. I work in the Chief Engineer's Office at GE Aviation, where I cover composites. And I'm going to give a brief overview in terms of how we use composites in our aircraft engines. At a very high level, we've been using polymer matrix composites in our engines for a little over 30 years now, and mostly for weight. We use them in the front section of the engine, our fan module, which is out here in the front, as well as the bypass cores. And clearly there's strong advantages in terms of the weight, but there's limitations in terms of how deep into the engine we can bring polymer matrix composites because of temperatures. And so that's why it's restricted to the front section. We've taken great advantage of PMCs over the years. Wonderful durability. I'll talk about that in a few minutes. In addition, more recently, we've been using ceramic matrix composites, mostly in the hot sections in the engine, basically back here in the combustor and the turbine. And the main advantage is temperature capability, because we can operate them hotter than we can metals, the nickel-based superalloys that we currently use. And that provides fuel efficiency for our engines. There is some weight benefit to the CMCs too, but the primary advantage is temperature capability. Over the years, we've been increasing the use of composites. As we started off in the 1980s, we're now using more and more composites as time goes on. Part of that is driven by the improvements in composite technology, but probably even more than that, the need for greater fuel efficiency has increased with both fuel price and also with just the other efficiencies in the system have come to the point where fuel is a larger and larger fraction of the operating costs of the airlines. And so because of that, we've driven to higher fuel efficiencies. One of the main ways that we can get fuel efficiency in the engine system is to go to higher bypass ratios, so more air going around the core than straight through the core. And that's driven us to larger diameter engines. And the one of the way, which also means that you have heavy engines, heavy front sections of the engines, in particular the fan module. And one of the ways that we can offset that is by using PMCs, because that is the cold section of the engine. And so it has driven part of the increased use of composites. I'm showing various applications here over the years for our composites in the engines. I'm not going to talk about all of them, but I'll highlight a few. The first major application that we had was this OGV composite, which is an alloy guide vane. It's a stationary vane in the bypass section of the engine. And we had it on our CF6 engines, non-structural part made out of carbon epoxy. It was really kind of a stepping stone for us, and based on our experiences, success we had with that component, it gave us the confidence in the 1990s to take a big step, which is to go to a composite fan blade, a carbon epoxy fan blade. Fan blades are the front blades as you look into the engine. It's a demanding application, sees a lot of impact debris, including bird ingestion. And so there needs to be a very durable, rugged component. It also sees a lot of fatigue loading. So we introduced that one in the 1990s. I'll talk about that in a few minutes. As we moved into the 2000s, another big step what we made was an all-composite fan containment case. This is the heaviest single component on the engine, so getting that into composites was a big weight advantage for us. And then, as I mentioned earlier, there's only so deep we can get into the engine with our current polymer systems. Certainly epoxies can get us so far. Then we look to higher temperature polymers, which includes polyimide resins. And so we do have a few commercial applications that we have for polyimides. One was the G90 center vent tube. And then more recently, a core cowl on our Passport 20 engine. We actually have a significant greater number of polyimide applications in our military engines. And then maybe lastly on this chart, highlight in the last 10 to 15 years, we've been very much focused on getting CMCs into the engines. Our first applications were in 2015, we had our first certified engine with a silicon carbide part, high pressure turbine shrouds, and then we also about a year later, I think we had our first oxide certified components on our Passport 20 mixers. So we move into the 2020s. Last year, we did certify our G9X engine, which has additional silicon carbide components, as well as a more advanced alloy guide vane made out of PMCs. Getting back to a couple of our premier applications, fan blades is certainly one. And as I mentioned before, we introduced it in the mid-90s on our G90 engine. And as I said, this is a very demanding application. And quite frankly, when we started down this journey, I think there was a lot of skepticism in terms of how well that would perform in the field. And in fact, it's performed extremely well. I mean, quite a bit better than all metal fan blades that we've used in the past and is used generally in the industry. So, on our larger engines, we have multiple versions now of the composite blade. It's the clear difference here is the complex geometry is getting more aerodynamic. That certainly is an advantage, but really most of the technology came from the aero side, not so much from the composite side. What's kind of hidden in this is there are continual material advances, processing advances, and design advances that are embedded in these different embodiments. So at this stage, we have this chart is probably slightly outdated, but over 120 million hours of field experience, 17 million cycles, which is flights. And like I said, there's been operation since the mid 90s and really excellent field experience. Then our second big application is the fan containment cases. I mentioned this is the heaviest single component in the engine. Its main duty really is to be there in case you did fail a fan blade. It's never happened for a composite blade. It does happen for metal blades. And, so it is a certification requirement. And so very much a high energy event. These fan containment cases have to contain that energy. And the resulting structure is fairly thick, somewhere on the order of 2 to 3 centimeters in some places. And it has some amount of thickness variation across the length. And that's the primary challenge, is make such a large, thick structure. And so we were able to make a composite fan case for our GNX engines, we've since continued on the GNX engines and also have a version on our latest engine, our G9X engine. So in addition to those major applications, we do have a variety of other applications for polymer matrix composites. Of course, we mentioned the fan blades, fan containment case, and I talked about the alloy guide vanes with respect to the CF6. But we have a lot of other components too, smaller components, but certainly have important functional characteristics. This pretty much represents what we have on our latest engine, our G9X engine. So overall, composites, as I said before, is doing extremely well in the field. I think really almost part by part, much better durability than the metal components. We do see some damage in the field. Erosion happens, hard body impact, bird strike, bird ingestion, and we have encountered some damage due to residual stress issues in some of our parts. And but again, overall, very much improved durability compared to the metals. We do look to continue to improve our designs and material processes. Moving on to CMCs. So, and as I mentioned before, the primary motivation for the CMCs is to get to higher temperatures. And so we can operate, roughly 500 degrees Fahrenheit or 260 degrees C hotter components with the CMCs than the metals. And what the metals we're replacing is nickel-based superalloys. They're about 1/3 of the density of the metals, so that's an added benefit, but the primary benefit is temperature capability. That really means that the gas temperatures are actually significantly higher than the material capability temperature. So the way that we normally manage that is we steal air from the compressor, cold air from the compressor, to cool our parts in the hot section. And that results in a hit on fuel efficiency. So by allowing our parts to operate hotter, we don't have to steal as much air from the compressor, and we improve the fuel burn. So as I mentioned before, our first certified components, high pressure turbine shrouds, which we introduced onto our LEAP engines. And we are now entered service in 2016. And we now, again, these numbers are slightly old. I'm pretty sure we have more than 2,000 engines in service at this point, and like I said, over 10 million flight hours in operation. CMCs are performing extremely well. And then our most recent certified engine, our G9X engine, which has not entered into service yet, but the engine was certified in 2020. It will be the engine on the new 777 Boeing airplane. And we have additional components. In addition to the HPT shrouds, we have combustor liners and nozzles, HPT nozzles. Future developments, we are moving into turbine blades, and we have run now multiple test engines with blades for a large number of cycles. Very successful, and we will be looking to introduce those in both our military and commercial products here going forward. So lastly, where do we want to go, and what are our future needs? Certainly, high performance materials in the sense of increased toughness and durability. We're always interested in that. As I mentioned, we're also, certainly on the polymer side, trying to continue to push the boundaries up in temperature. Unfortunately, we kind of get capped at polyimide operating temperatures. It would be nice if we had a material of some form which would get us into that middle range in between current PMCs and our CMCs. And then, really attacking cost through manufacturing improvements, It's always, and for PMCs, it always is a cost weight trade-off. And so the more we can attack costs, the more PMCs we can use efficiently. And then the last thing is really introduction of a new material. That's something, of course, that's faced the industry for a long time. There is a lot of cost in getting confidence and a database around a new material. So things around process modeling to help us with manufacturing implementation, as well as industry databases for material properties. So that's the quick overview of composites at GE Aviation. And sorry I couldn't be there in person, but hope you have a good conference. Thank you. Hi, I'm Scott Finn. I work in the Chief Engineer's Office.
So thank you, Scott, if you're listening or watching us. And yes, great insights into these hot topics, so to say. Now I would like to introduce our last speaker for today. And she will be live with us. So Clémentine Gallet, welcome to JEC Connect.
Hello.
Hello, Clémentine. So quick introduction, Clémentine Gallet is a mechanical engineer. She graduated in 1997 from the Technological University of Esslingen in Germany. Before, she did an IUT in mechanical engineering in Lyon, France. So from 1997, when she promoted to 1999, she carried out a large R&D project regarding a prototype sailboat of 6.5 meters by filament winding technology. And this was presented during JEC in 1999, so to close the project. And this won the prize from the Ministry of Research for the creation of innovative technology companies. So in logical consequence was that in January 2001, she co-founded the company Coriolis Composites with Alexandre Hamelin and Yvon Hardy. So the company quickly grew in staff, and 2006 saw the first entry to the market with some equipment developed for the Airbus R&D Techno Campus in Nantes. So in 2015, after strong growth of the company, Clémentine led a capital change operation with the entry of two major investors, BPI and ACE Management, to replace the historical shareholders and start a new phase of growth for the startup. And in 2018, Clémentine led the first external growth operation with the acquisition of MF Tech, which is a supplier, or was a supplier of filament winding robots. So Coriolis Composites is now a world leader in automated processes and software, with a partnership with Dassault Systèmes to manufacture high-performance composite parts. Currently, the company holds around 50 patent families, which protect the mechanics, know-how, and associated software. Currently, Clémentine is the president and CEO of Coriolis Group, which has 3 subsidiaries abroad, so Germany, China, USA, and of course, one main site in France. So today, Clémentine will present about composites automation, so the challenges of tomorrow in aerospace specifically. With 3 major points, we will be able to listen. First is ensuring high production rates, so the ultra-efficient means of production, always the balance between productivity versus costs, reliability and quality control. Second point will be about development teams, simulation tools allowing synergies of design and manufacturing skills. And last point, be greener, so how to integrate more materials with low ecological impact. Clémentine, the stage is yours.
Thank you. Thank you for joining this talk to everybody. So I won't present myself because you did it. I will start with a quick presentation of the company and then give a talk about the challenges of composite manufacturing technologies in aerospace. So let's start with a short presentation of the company. As said, Coriolis Group is made of two subsidiaries. One is dedicated to fiber placement technology, and the other one is to filament winding. Both are based on super high knowledge around materials, robotics, and software. The company is now 20 years old, so the group, and we have about 150 employees over the world. We installed 140 machines. If you take both filament winding and IFP machine around the world, I will give you some references just for you to know. So these are the name of our typical customers. The first line above the line is for fiber placement, and below it's for filament winding. So you see mostly aerospace company, but also some new cases for automotive industry, which is asking for high automated processes for composite manufacturing. So we are jumping more and more in automotive projects, but historically we are 100% aerospace driven. Just for you to have an overview of what can be done with our robotic systems, you have here a very versatile typology of parts. So from a nacelle, which is an inner fixed structure made by Safran in France and UK. This is a door of main landing gear. These are spars made in Russia for the MS-21. This is an application I will. This is a launcher part and a big. The kill beam is a A350 for Airbus kill beam made in Nantes in France. It's a huge part made with our robotic system. It's a bigger robot than the one that is doing nacelles, but still the same basis and the same know-how. Front nose for Dassault Aviation frames with premium aerotech and the bulkhead of the Bombardier C series, historically C series, and now Airbus 220. So this is a kind of part that can be done with our robotic system, and this is showing our experience in different type of part that can be studied and done with our machine. So we are starting a very early stage where the customer is asking for, okay, I can imagine I must bring automation in the manufacturing of my part, but please, Coriolis, help me to do it. And we are starting very early with our simulation software to allow it. And this is what I will show in the presentation, because we are involved in an end-to-end process with our customers, and we see now new challenges for automation in the coming years, especially in aerospace industry. And these challenges are about super high rates we have to achieve. And high rates doesn't mean decreased quality and reliability of systems. So we have to be super attentive to quality issues. Then we have a big challenge in digitalization. Even if we did a lot before, I think things has to change in the coming years. And it's a question of end to end. It's not just design, it's not just manufacturing simulation, but it has to be a full chain. And then how to be greener and safer, maybe a bit. So that would be the part of my talk. So at the first, how to ensure quality and high rates. So what we know is the next programs to come from the big players with a A and a B will be a super high rates program. So we are facing a situation where historically the automated system were dedicated to A350 with a rate which is more about 10 or a bit more than 10. And now we are talking about 60 or 70 plane a month. So it would be a huge step to achieve. And this has to really, we have to think about new systems, on automated systems that are more suitable for these high rates. So what does productivity mean in our technology, in fiber placement especially? It's a time to lay up a part without breakdown and microstops. So the manufacturing process is part of this, but not just. So if you take a manufacturing process of composite part, there are many steps to be done. But concerning the pure layup time, the parameters are said here. Number of toes. The toes are the slits of carbon fibers. The widths, the layup speed, the time feed and cut. So this is a big challenge for machine manufacturers. And the programming strategy. That means that how you go from a position to another one as fast as possible. So these are the parameters influencing the productivity. And how to address the next challenge to come. It's a question of playing with a number of toes and widths of the toes. So again, here you have a kind of simulation of comparison of different head systems. But at the end of the day, you need to plug that on your geometry to know exactly what will be the result and what will be the productivity to achieve. And we are talking about new rates of aerospace programs, and these gonna be small airplanes or single aisle maybe, or twin aisle, but still a bit smaller than A350 than before. So that means that we have to work on. We made a lot of benchmark on the manufacturing process of composite parts, and these show what are impacting the floor to floor. That means really the time you need for manufacturing a composite parts. And this show that a big issue is the quality. So again, starting in the start of my talk, we were talking about high rates, but without missing quality issues. And if you take this camembert, you see that inspection is really the key of bringing quality, and inspection systems has to be really improved and addressed by technologies that are really following these high rates issues. So if we stop the machine to inspect, then we lost the rate we want to achieve. So that's a big challenge for automation players in composite industry. And here you have all the rest. The layup of material is at the end just 24% of it. Then you have all this manual operation and cleaning and all that stuff. So for sure, we have to, with our customers, we have to focus on all of these issues. But mainly you see quality, inspection, and layup time has to be improved to achieve these high rates with the quality required by our aerospace customers. And this is a kind of online inspection we are working on. So there are many players working on this topic, and it's not so easy. So there are a lot of knockdown to be unlocked, but we all are working on it, and I think it's a key for the next generation of automated system to come, and for the next program, of course. So this is ongoing, and this is something that has to be solved. Then I will just give an overview about the simulation and digitalization of the end-to-end process of composite manufacturing for aerospace. Because we all know from the history of composite manufacturing that there is a lag sometimes between the design and the manufacturing. And this is not just due to simulation tools, it's also due to cultural issues and a bit of separate world between the design and the manufacturing. But at the end, if you bring the tools to the people, then you will get more and more in the loop of being sure that what will be manufactured, has been designed will be manufactured correctly, and that you will bring all the optimization that is needed for the manufacturing will be considered in the design phase and not after the machine is there or after the process is in the lab or in the manufacturing shop. So this is a presentation of the loop that is still missing in the simulation tools because of this separation between design tools and manufacturing tools. And for the next generation of high rates programs, aircrafts, we need this kind of iteration and to make sure that your production system will be super optimized, and even you can reduce the cost of it. So if you know exactly in the design what can be optimized, and then you make an iteration to make sure that the whole process will be optimized, then you can reduce the cost of it and ensure your return on investment of it. So this shows the design phase, the manufacturing phase, and this tool here in the middle is designed for manufacturing and is really helping the designers to better understand what will happen and what they can optimize to reduce the cost. And that goes until the toe widths and until that goes really deep in the parameters of the process. And this is a bit of not a revolution, because I think it's in the logic of our engineers of tomorrow, but still this is still to be done, and we are working strongly together with Dassault Systèmes and 3D Experience platform to make it happen in our IFP world. Then because it's already time to go, I will give a bit of overview of what can be done in environmental issues. And this is not just environmental issues. This is also a question of bringing a bit of better manufacturing processes coming from the materials. So we all know that the materials that are used today are based on epoxy resins. So mainly for fiber placement, I mean, is made of epoxy resins, and we really think that in the future we will switch to thermoplastic. We're all talking about thermoplastic since 20 years, since I am in the business, but there are still structural parts and primary parts are not made with this material, and this has to be really considered in the future and making sure that it happened. And even for the machinery that is behind, it's much easier to handle thermoplastic materials than epoxy materials. It's a question of tack and life cycle of the material. So this is something that has to be developed and make sure that it will really happen in terms of cost, in terms of mechanical performances and all that stuff. So, and for sure, if you are talking about material like carbon and robotics and filament winding, you are involved in H2 programs. So all the composite industry is moving in a greener aircraft on one side for the lightweight issues, and on the other side for new propulsion system and new energy system. So working on both is a really fantastic and super enthusiastic for engineers like we are. So that was my talk today. It's a bit short, but feel free to ask if you have any question, and even through the net. So it will be a pleasure to answer any kind of question. Thank you.
Merci, Clémentine. Thank you very much for this introduction to the automation in composites manufacturing, which is, even though you are working on it for 20 years, still a challenge. Lots of things to do, but we are getting there. And let me start with introducing or bringing back Ludger, because we have some questions. We could also ask him a few questions. So Ludger, if you can connect back. Super. So,
Hello.
Welcome back. So the first and the last speaker are here. The two other speakers from US won't be attending the question session, and I will make it short because we are running out of time with it. But maybe first question, and you mentioned it quickly in your last slide, Clémentine, is do you work mainly with thermosets or do you also look at thermoplastic resins, and why?
We are working on thermoplastic since the beginning because we really believe that there is no future for non-recyclable materials. So we are working on it since 10 years. We have partnerships with TPRC in Holland, with Fraunhofer in Germany, and working all together to make it happen. But it never happened, actually. So we are still waiting for it. It's too expensive. It's not the right performance that the aircraft manufacturers are looking for. So this has to come from the big OEMs, and then it will be done. But from our part, it's ready to use. It's a question of pushing the material manufacturer and pushing the OEMs also.
So great call to action, Clémentine. Hope there is some listeners today. Maybe Ludger. One question for both of you, actually. I was speaking with Ludger previously about functional parts, so increasing the amount of functions in one part through clever material selection. So maybe for Ludger, what is the main interest doing so? And then for Clémentine, could you imagine also laying a lot of different materials or composite materials over metallic materials, for example?
So the very first one is multifunctional in terms of that this tank, for example, is in the same moment the structure. So you know that reducing weight is always to get different functions, not only to have a container, but as well to have a function like a structure. But we are going further, as I presented. We would like to see functions like piping and structure. So it's integrated piping and structure, and especially when going to electrification and so on, like going for not hydraulic valves but electrical valves to have integrated umbilicals in the structure itself. You can't do it, or it's very hard to do it with metallic materials for sure, but it's easier. And I think you are working on that as well. Easier to do it multifunctionally when you come to composites, and then to make an indication. But when doing this, we are talking about not only multifunctional, but multifunctional by design. So this would be the very interesting part, because then you are not only putting on one side in terms of integration your structure in, and then you come with your, for example, umbilical, but you do it at the same moment, and then you have the right connections. And this is a challenge, but it helps us to reduce weight, and that's what we think.
Yeah.
So Clémentine, how can we make it happen on the machining side?
No, we are on it. So, but it's a demand coming from the automotive industry from our side. So, because composite is too expensive, they are mixing both and putting the right material at the right place, and that's our challenge now. It's to put super high price material, but the less as possible and at the right place. And this is, from the structural point of view, is super interesting projects, and from the manufacturing point of view, it's super interesting too, because you have to mix a metallic structure with a composite structure, and it's really amazing results. So we are mostly working with Stellantis. In France, we have a partnership nearby in Bretagne here, and it's really promising, and already maybe in the coming 2 or 3 years it will be implemented in a car. So that will be promising.
Excellent. Yeah, maybe one last question I see in the chat. It's probably interesting for both of you. It would be interesting to see also Scott's view on this one. So how to use actually thermoplastics in high temperature applications. How would you solve this challenge?
It's more for you, I think.
So I can't answer it too much, because when coming to high temperature, when we talk about high temperature, we talk about either about high temperature in terms of in terms of propulsion systems, or we talk about high temperature for return. So this would be very much a challenge to do it in this area with thermoplastics. But there are a combination when coming to outer skin and so on of solid boosters and so on. There are still some possibilities when you are in the medium range. So just talking about aerodynamics heating and not talking about propulsion systems. So, but to say it very, very simple, when coming to hot areas, we talk about degrees of 1500 degrees and up, and then we are not talking about thermoplastics anymore.
Sure. Also, thank you so much, Clémentine and Ludger, for your answers and for participating, of course, for launching this JEC Connect. At this point, I would like to thank also all of the attendees for the aerospace session. We hope to see you at the next conference session focusing on the automotive industry from 3 p.m. onwards today. In the meantime, take care and see you soon.
Yeah, and we have a booth in JEC Connect, Coriolis, with the team.
Are you best prepared? Perfect.
Oh, a little bit. Okay, so thank you very much. Have a good day. Bye-bye.
Thank you. See you. Bye.